Then the next speaker
Ladies and
is
gentlemen,
Dr. Paul O'Sullivan, and he's from the Cork University of Technology, and he will talk about designing airflows to minimize COVID transmission.
thank you very much.
If you wait 1 second.
Well, it's quite nice to look at.
Yes, it's beautiful pictures. Okay, the floor is yours.
Thank you very much, Peter. Thank you very much, Sue, for inviting me. Some excellent presentations throughout the day. It's amazing to be part of a panel with such a breadth of different unique speakers with all the different expertise and backgrounds, and I'm delighted to be here to make a small contribution. I'm going to talk a little bit about the room that Rod spends 12 hours a day in, single-sided ventilation. It's near ubiquitous in our buildings, yet it's a very vulnerable approach to ventilating naturally. I'm going to look a little bit at that, look at the relationship between that and health risk, and then look at one or two ways that we're investigating in our own group of how we might be able to improve those situations using airflow guiding components or components different to windows and so on. So my name is Paul O'Sullivan. I just want to acknowledge various different people have contributed to different aspects of the work in the presentation. So like I said, two aspects really. Look at for designers, just look at how designers who come from a ventilation background can deal with now the new need to evaluate health risk as well as comfort risk and climate risk. So is there frameworks or approaches we can use to assist in that? And then look a little bit at single-sided ventilation and one or two things we're learning about how that works, what are the airflow mechanisms at play, and how we might be able to exploit those. Just summary, I think we've seen a lot of this today. Reeve and Ashley have lots of good guidance, as do others. If we ventilate to meet the existing standards, then this could actually be more than adequate. So there's a performance gap here between what we say we do in design and what actually happens in practice in our building. So this performance gap, again, still exists, and if we can close that, I'm sure that can help. So direct airflow should be diverted away from groups of individuals to avoid pathogen dispersion from infected subjects. Use openable windows more than normal, even if it's at a comfort cost. So that's a question I think a conference like this can discuss and address. What's the trade-off between comfort and health, and where do we go with that? And 6 air change rates per hour has been identified as a recommended target for airflow rates. So in terms of evaluating long-range airborne infectious risk, if we think about the early design stage, HVAC engineers, architects, M&E designers, I was one for 11 years before I moved into academia. Traditionally, we've not been, we haven't evaluated or haven't had a need to evaluate airborne infectious spread at the early design stage. This is a pre-COVID world. Nowadays, that has changed. And about 80% of the key decisions in any building design happen very early on in the early design stages. There's a lot of vulnerability lock-in can happen when those decisions are being taken. So I think we really need to try and develop frameworks or tools or integrated approaches that allow designers to make decisions early on that are informed. Obviously, later on in the design, they can use detailed simulation, but at that point, I feel it's almost too late. Some of the big calls have been made in terms of the morphology of the building, the architectural form, and its relationship with the microclimate. So I won't go into all this, but we developed, or we're working on a kind of a 3-stage approach to embed the infectious risk check with ventilation rate modelling. So stage 1 really just covers what you would the standard work as a natural ventilation designer. You would take your various design criteria, your static sort of capacity sizing scenarios. You would look at boundary conditions, you would opening details, building information, room information. You would feed that into your airflow rate models. Out of that, then you get your infiltration rate, flow rates or calculations. You get your volumetric or purpose-provided flow rates. Once you have that, then you'd move probably onto overheating analysis or evaluating comfort or looking at cooling. But really, we need to insert a kind of a stage 2 now, looking at infectious risk checks. So we take those flow rates and feed them into a model. We took the Wells Riley in this instance and feed that in with many other parameters. Evaluate whether the probability of infection is high or low or acceptable. If it's not, maybe you need to go back. And rather than taking just a static input, assuming that you can have 6 air changes, as we've seen, that's not a reality. We need to make some attempt at modelling those based on boundary conditions available. And then stage 3, we're used to doing seasonal checks. For example, looking at overheating over the long term. I think we should look at the same for reproductive numbers over the long term, for example. So taking weather files, doing a little bit of work with those and actually allowing us to check, is there some seasonal effect on infectious risk associated with boundary conditions through the winter and the summer. We applied this approach to a study in Cork. It's a lecture room, it's single-sided ventilation. So we looked at 7 different retrofit scenarios. They were influencing the infiltration, but also the ventilation. Top hung outward windows was one or two of the scenarios. Then we had some louver designs. As you can see here in figure 5, this is a part of the building we've already refurbished, and we have a louver-based strategy there. So that informed what we were proposing in the retrofit scenarios. We came up with about 8,000 combinations that we evaluated, and that was really based on different occupancy levels, different exposure times, different masks and so on. So we put that together, and as ventilation engineers, we wanted to understand, well, is there a higher or lower risk with different strategies? And what we found really was that if you retrofitted single-sided ventilation can perform well, but it does need some complementary measures at times, depending on what boundary conditions you're interested in. You might have a low delta T at the opening, so low buoyancy-driven flow, or you might have low wind speeds. In those situations, you need some additional measures. The existing MV system had window restrictors to stop people like myself and Rod jumping out the window, as we said. And as a result, you actually had a very low effective opening area. And then that meant that you had a low performance potential for those systems. So those sort of design decisions need to be discussed or looked at, I think, closely. Demand controlled mechanical ventilation was an option we had, and that was very effective, but it wasn't necessary all the time. NV under most boundary conditions was more than adequate. The big outcome is that the boundary conditions play a significant role in NV. It has got a stochastic, intermittent nature, and when you design based on one criteria, that doesn't necessarily translate across the year what you will see in practice. So there's a big intermittency issue with that. When we looked at the seasonal RI, not sure if you can see that very well there, but we looked at 4 cities in our study, and a designer would look at one location. Typically, they're designing a specific building. And here you have 3 rows. Each row is a different ventilation scenario. The existing one is on the top, and you can see a lot of RI numbers greater than 1. These are daily average RI numbers. Whereas when you retrofit your ventilation with a larger opening area and a better coefficient of discharge, you actually can get significantly improved performance in that regard. But there is a sort of a boundary condition-based seasonality in the likelihood of infection. So winter and summer at different times of the year, you'll have different levels of performance. So upgrading your NV can reduce risk, but it's not going to eliminate it entirely. And you need to evaluate your designs under a range of different boundary conditions. You can't just look at a single worst case or best case scenario. In summary, really, early stage design frameworks for risk checks, I think if they're integrated into existing NV practices, they'll be used and they'll be essential and very valuable to designers. Single-sided ventilation with one opening, it worked well and it could suppress airborne transmission based on the modelling. But in practice, mixed mode approaches can definitely help address intermittency of boundary conditions. So that's something that needs to be on the table and discussed as part of any design, how you can achieve that sort of backup planning. If we talk about resilience, we need recoverability plans in the event of failure. And so we need to figure out really how we're going to have those recoverability plans for NV systems. So I just wanted to touch then a little bit on a couple of different aspects of single-sided ventilation as a strategy to ventilate spaces. I won't dwell on this very long because we've had other speakers talk about different strategies. Cross ventilation, as we saw with Rod's work, can deliver significant air change rates. It's not the case with something such as single-sided ventilation. It's quite vulnerable. It's low maintenance, it's non-invasive, it's occupancy-centric, it's quite resilient, but it does have a performance issue. So it's about overcoming that, and some of our best available models currently don't perform very well in predicting single-sided ventilation. That's not coming out great, unfortunately, just with the background colours, but what we're seeing here is really just talk for a second on what is the airflow exchange mechanism in a single-sided ventilation application when you have only one opening. Effectively, you have a shearing layer that develops, or a mixing layer, as a result of a turbulent jet that develops along the opening. This is when it's wind-driven, and the flow is typically parallel along the facade. And that shear layer actually has a number of different mechanisms that contribute to exchanging air. It could be the penetration of eddies from the shearing effect, turbulent diffusion, or at times you can have a pulsating flow. The figure 9 there on the left is actually measurements we've done where we've measured wind directions and magnitudes at the local Met station, at the building height, and at the opening. On the right, the B is at the opening. Irrespective of the wind direction, we saw the flow was always parallel at the near facade, and that shearing layer was present as a result of that. But how do we take that, and exploit that? This is really just some other measurements we've done on single-sided on the left, where we had a number of different openings in the same room. We tested different openings, and again, we had ranges from around 1 up to around 6 in terms of air change rate potential. A big issue with single-sided ventilation, though, is the short-circuiting effect. If you think about the mixing layer as it passes parallel along the opening, not all the air that enters into the window actually contributes to aerating the space. So if you do a velocity-based calculation, you'll find that about 40% of what you expect as an air change rate short circuits and doesn't contribute. So that's something that we're looking at to try and exploit or deal with. Before I get on to that in the next slide, we did some measurements on different window designs. There was a lot of conversation today about window opening versus natural ventilation design. And we looked at 7 different window configurations in the lab following our field-based measurements with parallel flow. And we found, even if you look on the far right here, you've got a side-hung inwards opening window. And depending on the orientation of the flow at the window itself, you could have up to 400% difference in the air change rate. So it's very challenging to generalize natural ventilation at times. A study in one application may not translate easily to another situation, even on the same facade or in the same building. So it is a big ongoing challenge to find generalized recommendations around this. This is just some work we did because we wanted to understand a little bit more about parallel flow. Is it always horizontal? And we've done some large eddy simulation modeling, and we found that the front here is the windward and the rear is the leeward, and that the flow, in fact, is actually an upwash, downwash, or transversal. So the flow has different directions depending on its relationship to the actual stagnation point in the building. So if you're locating a room at the top floor or the bottom floor, or at the side or the center, you actually have a very different sort of boundary condition taking place there. So again, trying to generalize the source or the basis for the ventilation rate itself can be tricky. So we went a little bit further, and I'm not sure if they're coming up well, but you can see here on the left, this is a 3-story building that we've done some simulation work on. You can see on the top floor, we get this lovely upwash effect, but below that, then you get this downwash effect. So you've got this different orientations of how the flow enters into the space. And on the right, you have the plan where you can see the mixing layer in horizontal view, but in fact, it's got a very much 3-dimensional nature. So trying to actually exploit that in terms of designing components, but also in terms of making predictions, is an ongoing challenge. We've done a little bit of work on airflow guiding components to try and, again, improve these poor ventilation rates that we see. We don't believe that windows are designed with aerodynamics at the forefront. They're often designed with for other reasons, and then we just use them as aerodynamic components. So we looked at 2 different types of louvers and compared them to a plain opening aperture. And what you're seeing here is the age of air inside in a simulated space. If you look at the top row, it's a windward condition, and we see that by adding the louver from the left to the right, the plane to the louver situation, we significantly reduce the time that the air is residing inside in the space. So we're significantly improving the air exchange efficiency effectively. However, if you follow that middle column down to that same louver in the leeward application, it actually makes it worse. So if you take a louver, you have it in a windward condition, it performs very well. If the wind direction is changed, it's now performing not so well. Generalizations in natural ventilation are very difficult. We then developed the prism design, we call it, so it's just a prototyping design trying to explore what's happening more. And we found that when we have horizontal and vertical fins in place, you can see on the far right column, we improve in all situations. You get an improvement in the air exchange inside in the space. And I think what's happening here is we're actually breaking the mixing layer, the short-circuiting effect. So the louver actually creates an inflow and outflow that's more pronounced or defined, because in single-sided ventilation, the single opening acts as the inflow and the outflow in that scenario. So what we're doing here is breaking that mixing layer and trying to upset that short-circuiting effect to allow a direct airflow path into the room and out of the room. So we see about a 31% improvement, or up to 31% improvement in the modelling work. We've done some measurements and field studies on louvers, and we found anywhere from about 6% to 50% improvement. So we've seen this translate to field measurements as well, but it's an ongoing process. But it is a way I think we can look at better air change rates and ventilation rates that may lead to minimising transmission. So just, I'd say, how are we doing on time? Okay, so just a summary on that part very quickly. So trying to achieve 6 air change rates with single-sided ventilation is going to be a challenge, and doing that consistently. Short-circuiting effect is a problem, and that can be addressed with certain airflow guiding components. We believe that they break the mixed layer and then enhance the airflow rates and give a better direction of the flow into the room, because if you think about coupling internal-external flow, we find that the jet at the opening is strongly linked to the actual movement, air movement inside in the space itself, in the secondary flow. And generalization is an ongoing challenge. Studies are needed, but at times it can be hard to generalize the findings for different locations and different buildings, and that's an ongoing issue. Just one other thing I wanted to touch on, which is another recent development with single-sided ventilation, but with more than one opening, is pumping flow. Is not work I've been doing, but it's work some of my colleagues in Lisbon have been doing work on. And this seems to be very promising, again, where when you have more than one opening and there's a sufficient separation in those apertures, you can actually get what's called a pumping flow effect. And it brought to mind Roger Curtis earlier talking about the air pump ventilator from Robert Boyle, and that we're back there again looking at pumping flow. The oscillatory nature, the periodicity of the flow here is linked to the vortex shedding on the building itself, and it can significantly improve air change rates in single-site applications, upwards of about 123% at the moment in the literature. So it's another technique I'm not diving into too much, but it's another one of these advancements I think that can contribute to better airflow performance inside in buildings. So just in terms of some overall conclusions, so boundary conditions, opening geometry, and the near facade flow, these all have a strong influence on primary and secondary flow, and we do need more work in those areas to be able to give better guidance on what the likely performance will be at the design stage when buildings are constructed. Designers do need simplified but robust modelling frameworks at the early design stage, and evaluating health risk is relatively new given the changes with COVID. Traditionally, that wouldn't have been in the remit of comfort, heating, cooling engineers and M&E engineers and so on. More work is needed to better understand how complex flows can be easily modelled in analytical tools, because tools like CFD are very useful, but they're time intensive and computationally intensive as well. And they're not always necessarily the best choice at different stages of the design of a building. And single-sided ventilation can be enhanced using airflow guiding components or phenomena such as pumping flow. So that's it really. It was just a sort of a whistle-stop tour on a few developments in a specific type of ventilation application. So thanks for listening.
Okay, thank you very much.